Hello guys, welcome to this tutorial. We're going to build a bootloader. This bootloader can be used to load an operating system into memory. I think I will make this into a full tutorial series. We'll start from the bootloader and then we'll get to operating system things. Today we're going to start with our code. We will be booted into memory. We will play with a few interrupts, we will write things at the screen, and it's going to be very interesting. So, let's get right to it. First of all, you need a Unix operating system. Generally, any Linux distribution will do as long as it has a package manager that will make it easy for you to install our necessary programs. The first one is an assembler. An assembler will create a binary from our assembly code. I suggest the flat assembler or Fasm. You can also use a net-wide assembler or NASM. Both are very good. The syntax is almost the same. There are a few differences. You can use either. We were going to use Fasm in this tutorial, but I will write on the video description the commands you will need for the NASM assembler. If you have any syntax issues or any issues or comments or suggestions, please write them on the comments and I will help. So, we need an assembler. The next thing we need is an emulator. We're going to start with Qemu. Qemu is a very good emulator that will we will load our bootloader with this one. We will not use a real machine today. And then we are going to continue with Box. It offers a lot of opportunities for debugging, so later we're going to use Box. I will post also on the video description the osdev.org website. It contains a lot of very useful information for operating systems, and also I will post some of the BIOS interrupts we're going to use on this video. So, let's start. The first thing we're going to do is, basically let's explain the boot process a little bit. So, when we turn on our computer, the BIOS will search for a boot sector. A boot sector is the first sector of any drive that has the last 2 bytes of it as 55AA. When BIOS finds a 512 byte sector with the last 2 bytes as 55AA, it's going to load us into memory on address 0x7C00. This is our address in memory where our bootloader will be loaded. So, when you write assembly, always write comments. So, origin address 0x7C00. The next thing we're going to do is every sector is 512 bytes. Of course, we're not going to write 512 bytes. Our code is going to be much less than that, especially at the beginning. So we're going to pad everything else with zeros. So we're going to use the times 510 minus dollar minus $, db 0. So this will pad everything with zeros. And the last 2 bytes from the 512, we're going to write them as 0xAA55. Before I said the last 2 bytes need to be 55AA, hexadecimal. But because it's going to be x86 uses little endian, basically the least significant bits are read first. So it's going to be read as 55AA. Now let's save our file. Let's go here. Let's clear our screen. I did some tests before. So let's assemble our file, fasm boot.asm. we see that a 512 bytes file is created. Let's use Qemu. This command is Qemu system i386 boot a-fda boot.bin, and once we press it, we see we're being booted from a floppy. Let's quit and let's write a character on the screen first of all. To write a character on the screen, we are going to use the 0eh of interrupt 10 command. So we are going to put into AH register 0eh. We are going to put the character we want to write into the AL register, and we're going to print this character on the screen. So let's do it. So move AH 0EH, move AL 10, move AL, let's say the P character for print, and then let's call interrupt 10. It should be hexadecimal 10, not decimal 10, hexadecimal 10. Let's put some comments. So BIOS function to write on screen, character we want to print, BIOS interrupt. So let's assemble our file, Fasm boot.asm, and let's emulate. So you see the character P is printed, but let's clear the screen. We see a lot of things that we don't need, so let's clear the screen. In order to clear the screen, we're going to use the scroll function. If we check, the scroll function is this one. We put into AH 06 hexadecimal. Into the AL register, we put 0 to clear the entire window. Here in the BH, I know it's written differently. Basically, we'll write the color we want our characters to be, and then we'll define the row and column. Our screen basically is 20 by 80. We want to set the beginning, the left upper corner, and the lower down corner. So let's do it. Let's set some comments. Clear the screen. So we're going to move into AH 0x06. This is the BIOS function to scroll. Then we're going to move into AL 0 or 0x00 to clear entire window. Then we're going to set the color into BH. We're going to set 0x07, which is light gray. And then we're going to set the start of our upper left corner, basically 0, into CX. Move CX 0x0000, upper left corner, and then we're going to set the lower right corner into DX. Move DX 0x18 for F. And I will explain this right now. And of lower right corner. Now, why 0x18 for F? The screen size is 25 by 80, and 18 is 24, and 4F is 79. So we're basically going at the end of the screen. And then we will call interrupt 10. 0x10. Remember, don't write 10 in decimal, it has to be in hexadecimal. So BIOS 10 interrupt. After we clear the screen, of course I forgot, we need to jump infinitely. After we clear the screen, let's set the cursor position. We want to write at the beginning. So, in order to set the cursor position, let's check this command. It sets the cursor position. We put 02 hexadecimal into the AH register. We set the page number, which is going to be 0, and we set the row and column, basically. We're not going to use graphics mode right now. So, let's go and set cursor position. So, we're going to move into AH 0x02, and this is the BIOS interrupt to set cursor position. Then we need to set the page number. So move BH 0x00, set page number. After that, we need to set the row and column into DH and DL register. So move DH 0x00, and this is the row, and then into DL move DL 0x00, and this is the column, and then we call interrupt 10. So let's check our screen now. Clear, assemble, then we use Qemu, and our screen is clear. Good. Let's write a character on the screen. Write a character on the screen. So, to write a character on the screen, we're going to use a different command. We're going to use the 0EH command. We're going to put it in the AH register, and on the AL register we're going to put the character we want to write. So, let's go and write move AH 0EH BIOS, here it's a mistake, it should be function. So, BIOS function to print a character. We're going to put into AL the character we want to print. Let's set P for print. Character we want to print. And then let's call interrupt 10. BIOS interrupt. Let's save our file and assemble Fasm, and let's emulate. You see the character P, I don't know how clear it is, it's quite small, is printed on the screen. So, what if we want to print a string, a whole string on the screen? Of course, it is not that simple, we cannot write something here. This is going to be an error. We cannot put a whole string in the AL register. If we try to assemble it, you see we are not even allowed to assemble it. So no, we're not going to do like that. We're going to use a register. We're going to put the address of a string in the SI register, and then we're going to print each character, and then we'll increment it. We'll print the first character, we'll increment the SI register, print the second character, and we'll continue like that. So let's do it. We'll create a function, basically a routine. We're going to call it print underscore string. So here we're going to call the print function which we are going to create now. So print is going to create a loop. The first thing we're going to do is load SB. This command will take what SI is pointing to and put it in the AL register. So will compare then the AL register if it's 0, if it reached the null terminator. Check if we reached the end. If we reach the end, if it's equal to 0, jump equal, that's what this command means, we're going to go into done. Let's create done, done, and here we're going to return red. In any other case, we're going to call print char and then jump back into the loop. Let's create the print char, print char. Here we're going to do what we did before. Move, let's scroll it a little bit, move AH 0 EH, and then call interrupt 0x10 and return. And after we call print, let's return here too. So let's try our code. Here, let's move, let's create a string first. We will write a name. It's basically a label, it's not a variable. We can call it hello test string. It's going to be a series of bytes. Hello from Bootloader, and we're going to end it with a null terminator. So we want si to point to the address of that string. So move si hello test string, and then we're going to call print string. Let's test our code. Clear. Fasm. Illegal instruction. Done. Let's see what we did wrong. Done. Red. Jump loop. Call print char. Jump equal done. Compare AL. Load SB. Print. Let me check the error message again. Done. Process done. Error illegal instruction. I forgot the. Okay. So, Fasm, boot.sm, good. The file is assembled successfully. Let's use Qemu, and we see our string printed. Of course, we see P printed too, because it was there from before. So, let's comment this code here. Okay. Now, what will happen if we print a second string? Let's say, for example, welcome string. DB welcome. And we end it with null terminator. So let's say move si, the new string, welcome string, call print string, clear, Fasm, successfully Qemu, and you see the new string is printed right after the previous one. We want it to be right under it. So let's do that. In order to do that, we'll go on the first string we created, and we're going to add a few characters. 0xa to go under the previous string, and 0xd to go at the beginning. So, and then of course we end it with null terminator. Now, if we assemble and we emulate, we see it right under the other one. Good. So, we let's add a few comments here. Read character to AL and then increment. done, print character, and then jump back into the loop, and basically that's it. We reached null terminator, finish. Okay, I think this is a good beginning for our bootloader. The next thing we're going to do is we're going to read from disk. We're going to set a second stage bootloader, because here we have only 512 bytes to use. We cannot do a lot of things on this file. So this will load our second bootloader, and on the second bootloader we can do anything we want. I think soon I will start posting lessons, tutorials on assembly language. I will continue with this tutorial. We're going to create an operating system and load it into memory, and we're going to enter protected mode. We're going to do a lot of interesting things. So please like and subscribe, and I will be very glad to see you soon.